You ever tried finding an old photo on your phone, scrolling endlessly through thousands of images, and thought, there's got to be a better way? Well, what if your phone just knew what you were looking for and grouped similar photos together automatically? That's the magic of locality-sensitive hashing, LSH for short. It's a technique that allows computers to quickly find similar things without having to search through everything. Now, we use search every day, whether it's Google finding websites, Spotify recommending music, or Amazon suggesting products. But here's the problem. Comparing everything to everything is just way too slow when you're dealing with massive amounts of data. Imagine trying to find a specific book in the world's largest library without a catalog. That's the challenge we face in big data. LSH, however, works like a secret shortcut, instantly grouping similar items together so we can find things way faster. Think of it like this. If traditional searching is like flipping through the pages of a book to find a quote, LSH is like having sticky notes already marking the important sections. Instead of checking every single entry, it jumps straight to the relevant ones. That's why LSH is used in image recognition, fraud detection, recommendation systems, and even DNA sequence analysis. But don't get too comfortable yet. There's a twist. Traditional hashing, the kind you might know from things like passwords or cryptography, is totally different from LSH. If you assume all hashing is the same, you're in for a surprise. In the next slide, we're breaking down what makes LSH unique, how it works, and why it's one of the coolest tricks in data science. Hash functions are like a secret code for data. You take an input, put it through a mathematical blender, and out comes a unique, fixed-length string of characters. It doesn't matter if you start with a whole book or a single word. The hash function always gives you a specific-sized result. Sounds cool, right? But here's the catch. Not all hash functions are created equal. If you've heard of cryptographic hash functions like SHA-256, you know they're designed for security. They work like a digital fingerprint. Tiny changes in the input completely scramble the output. Imagine writing your name on a piece of paper, then someone shuffles the letters so thoroughly that not even you can unscramble them. That's great for security, but terrible for finding similar things in large datasets. Locality-sensitive hashing flips the script. Instead of making sure that even the smallest change leads to a completely different output, LSH does the opposite. It's designed to hash similar things into the same bucket so they're easy to find later. Think of it like sorting socks. You wouldn't put all your clothes into one big pile and hope to find matching pairs. Instead, you throw all the blue socks into one bin, all the black ones into another. That's what LSH does. It groups similar data together, making search and retrieval way faster. But wait, if LSH lets similar things map to the same place, doesn't that mean we might get collisions, situations where different inputs end up in the same bucket by accident? That's a real challenge, and one we'll tackle next, because while LSH is powerful, it's not perfect. Up next, we'll see exactly how it works and why it's such a game changer despite its quirks. Let's say you're running a massive lost and found service, but instead of just one city, you're handling lost items from all over the world. If someone loses their keys in New York, you don't want to search through every lost key in existence. You need a way to quickly find the closest match. That's exactly what locality-sensitive hashing does. It helps computers group similar things together so they can be found faster without checking everything. Here's the trick. Instead of hashing data randomly like a normal hash function, LSH is designed to make sure that similar items get similar hashes. Imagine sorting a crowd of people at an event, not by name, but by something more useful, like their favorite music. If a group of people all love rock, they go in one section, pop fans in another, classical lovers over there. LSH works in the same way. It creates groups where similar things end up in the same place. This is done using multiple hash functions. Each one creates a different way of sorting the data, and when we combine them, We get a powerful way to separate items while still keeping similar ones close. It's like sorting a library by genre, author, and publication year all at once. Suddenly, finding that mystery novel from the 90s gets way easier. But what happens after everything is sorted into buckets? That's where the real magic happens. Instead of comparing every possible item in a dataset, LSH only checks within the relevant buckets. That's why it's so much faster than traditional search methods. However, this shortcut isn't perfect. Sometimes items might end up in the wrong place or we might miss a match entirely. So what's the catch? What are the real-world challenges of LSH and how do we deal with them? That's what we're looking at next, because while LSH is powerful, it's not immune to errors, and knowing where it falls short is just as important as knowing how it works. Locality